Welcome back to our second day of the school. And it is my pleasure to introduce you to Huey-Wen Lin, who I met a long time ago when I was postdoc at Columbia University. It's an age ago. And then I met her again here at JLab when we were both postdocs. So it's a pleasure to have her back. And she will tell you a lot of things about Lattice QCD, but this will be a sort of an interactive lecture. She will start with a 45 minutes of lecture, but then the next 45 minutes will be hands-on on a laptop. So I will let her tell you the details, but we will need a laptop every 2 or 3 people. So maybe if you do not have your laptop and you can go and grab yours at the ResFac, it will be great. If you don't have it and you are far away, it's fine because you can find somebody else to work with in the next 45 minutes. But I will let Huey-Wen take it from here.
Thank you. Okay, can you hear me in the back? It's good? Okay. Hi, my name is Huey-Wen Lin. I know it's really hard to pronounce my name. You can feel free, just call me Dr. Lin, Professor Lin. That's much easier, which I encourage most students doing. So since we're going to spend quite a bit of time together, I thought I'd just kind of tell you a little bit about myself. I'm from a small town in Taiwan. And so for most people, they don't quite know where that is. So it's not exactly China. It's a complex political issue we don't want to get into for the class here, but it is sort of its own republic system. We got our own president's election just a few weeks ago. That might pop up in the news every now and then. I got my PhD in Columbia. My preferred pronoun is she, her. And I was since New York, which is a great place for somebody who never out of the country to be, because it's such a diverse city. You can find all the culture there. So if I feel like homesick, I can find some Taiwanese culture somewhere in the city. That's great. But a lot of people hate it for a different reason too. So it's not a city for everyone. But for me, that's a blessing. And then since then, I moved here for my first postdoc. That was like a huge culture shock for me. I had never been in the South. But I was kind of walk around. It's kind of interesting. I did a lot of interesting things that I never done before. I had to actually cook. So my mom was really happy. I had to call her because now I cannot find the food I like. So I had to make it myself, which is again, another sort of growth. I get into bird watching around the area, which is great, a lot of nature here. And so it's just very different, some adjustment at first, but I think I kind of made most of that and I have a lot of great science here. And just like it's really, really great with a lot of activity going on. And I kind of get into hadronic physics because I'm here. So a lot of talk that I'm going to talk to you about is a lot of what I have been doing since I was here. And then I kind of continue and explore and then my own stuff like that. Yeah, and then after that, I moved to Seattle and then the Bay Area. When I first got the offer from Michigan State, I was like, oh, great. I have no idea how to deal with snowstorm. And I was really worried about all that because, yes, people keep telling me, I got lots of snowstorm in New York, but people who live in the city, you never have to shovel the snow yourself, right? There's always somebody doing the job for you. You always have a super doing all the work for you. So that was like a lot of worry about how to deal with the snowstorm. But again, I survived and I think I'm doing reasonably well. It's my 8th year at Michigan and we are again, go to love it in general. And then like many women in physics, I also marry a PhD. My husband is also a physics PhD and you can tell from the crazy hair as a proof, and that's our 2 daughters. So we also work around a bit our many body problem in a way. And then, so I hope many of the women, I really glad to see a lot of female students here. I hope like, it wasn't like that when I started. Every time I went to like a summer school, there are very, very few women. So it's really great that we see so many women here. I do all the embarrassing mom things as well. So we have a Nobel lecture in our university before COVID. And so this is one of the neutrino Nobel Prize. And I was, embarrassed myself taking picture with my kids. And then we start doing a few things like in our field called Lattice QCD. It's like a theoretical and computational physics. Both fields have very few women. You put them together, you have even fewer women. So we're starting in some of this activity. Now we have an annual event at the annual conference because there's still the issue kind of going around. And then there are some things that we are doing at Michigan State is bringing the idea that's organized by APS. So if you haven't heard of that, you can look it up. There are a lot of nice things that's going on that you can bring into university. The trick is really not to reinventing all the things that people already work on. We all have our job. We want to do physics. We don't spend so much time working about that. And the idea is sort of like, you try to put together resources, different university who facing similar problem, and you find what works for you and what doesn't work for you, right? So you don't have to reinvent all the things that people already worked out before. And unfortunately, like diversity issue, like every time I look into literature, I just find like a lot of things that people have talked about 30 years ago, sort of still things that's going on. So there are a lot of resources out there. And then my research is mainly in quantum chromodynamics, short for QCD. So you can learn quite a bit of that in this summer school. And what I do especially differently is I use high performance supercomputer, right? So I'm trying to target the problem that you are not easily done in the perturbation calculation, and so that I can contribute to the science in my own unique way. And I'm especially focused on the degree of quantum gluon in the hadrons, and we are trying to improve our knowledge in terms of property of some of the fundamental hadrons like nucleon, pion, etc. And so myself have quite a bit of journey to become where I am right now. When I was in college, I wasn't even thinking about getting the PhD. I wasn't quite sure what I want to do. And then I'm glad I have a professor tell me that I had to apply for grad school, which I did. And I specifically tell me to apply for Columbia University, which I wasn't going to because I know a lot of excellent students before me, they never got admitted by Columbia. I was like, why do I want to waste the money? Columbia is one of the expensive ones. And I didn't have a lot of money at the time. But then, yeah, then I did apply just sort of like, I want him to shut up, so I applied. And at the end, I got in. So again, I guess the lesson here is listen to your professor. They know what they're talking about. And then I guess if I never got into Columbia, I will probably never do what I do. And then I will met all the people I met and then so on. So there's a lot of cosmos things going on. And yeah, so then I realized there are actually a lot of people like me who wasn't quite sure, what this is a path or like what the light is like as a physicist. So some of my students and myself starting a podcast, and we start with interview a number of people about how they get there. And surprisingly to find out my experience is not quite unique. A lot of physicists, there are people who probably want to be physicists when they are 5 years old, but a lot of people won't actually. And that question is actually larger than I thought. And that was quite interesting by doing this podcast. So if you are interested, so there's a QR codes, and then the season 3, if you are particularly interested in nuclear physics, we are following a nuclear physics long-range plan. This is like a community exercise that community get together and say, what is important for our community that we have to build, we have to support so that we make really great progress for long-term future. And so we follow a number of people along the way. In addition to talk about their journey, we also talk a little bit about such a process that might become relevant to you in another 5-10 years when you graduate and start contributing to the field. So I summarize what I do in a way, sort of like as probably the heart of matters. And so basically it's something we all learn how to do as a baby, right? We're always curious about things, we smash them. And when you go out to be after your PhD and work with thousands of physicists, you can smash things with much better style. And if you do a good job, you even some people get Nobel Prize for smashing things. And so this is, if you haven't seen this, this is LHC. This is one of the biggest machines we built as an example, right? But there are still a lot of things going on in the US. And so They are ongoing. This is something that's going to be more relevant to you. So the machine, what we call it, ultimate QCD machine, it's like a microscopes. So electron ion collider, which is likely going to hopefully come online on 2030s. That's where you guys will be out there and actually doing exciting sciences. And there are currently some website. They are a little bit about what we write in terms of white paper for the long range plane just come out not long ago. And so if you kind of want to take a glance of the QCD part of such a long range plane, you can look up it's very long, but they have covered a lot of broad topic. That could be something you are interesting, something you might not know, you might find it interesting later on. So you can kind of explore that as well, right? And so I'm really clumsy as an experimentalist. I tried actually 2 years as a condensed matter experimentalist, and I realized I hate it. And the reason I get into is sort of like, that's the only research I ever done when I was undergrad. And I said, I did not know what I was doing. I had professor come to me and say, what do you want to do this summer? I was like, I have no plan. And so I just get into the lab and I learned to do some superconductor, but later when I get to the grad school and I realized, no, I don't want to do it and I will be miserable. And then I had to make a decision like, I can get into academia very quickly, but doing something I don't like, or I will switch the field. So I decided to switch the field, which is, add up to a few years to my PhD, but I think I'm doing okay, I guess. And so since I'm not good at that, and so my research tool is like basically computer. Again, it's not one of those things that I originally want to get into when I get to Columbia. A lot of professors was telling me like, oh, there's a lot of things you can do with a computer, but I never write code before. I don't have coding class in my undergrad. I had to write 0 lines of code ever. So that's not something like, it doesn't seem very attractive to me, right? But then later on, I did try out and I realized that actually I can do a reasonable job and contribute as well. So that's what I've been doing since. And so what we do is we use a lot of machines, and those supercomputer is like skyscrapers. Now you have number one. That I think Fuzuki was the number one a few years ago. They got outrounded by other people, so you kind of have to keep checking on the website to see who is the fastest and so on. But it also make it really exciting because that means that people care, right? The people care about computational calculation in pushing the science frontier. So it is a very exciting field. And a lot of people are putting money into building a lot of supercomputers to do various different things. So, all right, so we're gonna spend roughly 3 days here. And so we have quite a bit of things going on. And for me, after teaching at MSU, I'm a firm believer of like, I don't think sitting in a lecture made me feel like you heard a lot of things going through your brains and you feel very satisfactory at the end of the day. But then I don't think that knowledge actually lasts. So what I really like and also encourages also the student in my group, right? But really by learning by doing. And so I would give you a few examples, and then we will try to work on small group and try to kind of like deal with some of the hands and bits of some of the data that you might be seeing from Lattice QCD calculation. We will do a few of the like a standard things that everybody does. We use some statistical tool called Gen9. So we will kind of work on that a little bit. And then we will do kind of read in some data and try to extract some methods in some simple ways. And so that's, and I do want to emphasize that if you don't have Python experience or it's getting rusty, it's okay. I would really suggest you focus on thinking about how to do the problem, right? You can still think about the problem. How will you do the problem rather than, focus on the coding that you can catch up that later when you have more time. I do also have a few of the tutorial if you want some quick review of them more later on. But one thing I do like to emphasize is that you don't have to feel like if I give you 4 notebook today, I don't want you to feel like you have to do everything but not really understand anything. I think it's more important you take your time to go through each of them because you are actually learning for yourself. You're not learning for me, right? We don't have grading here. So if you don't finish it, it's fine. But how much you learn and then how much you stay with you, that's for you. It's not for me. So I don't want to take your time. We will be working in group. I'd like to have some discussion. And if you figure out things before other people share your ideas. And even though sometimes you might be able to surprise to learn about different ways of solving the problem. I often find like when I discuss problem, when I was a grad student, discussing problem with my advisor who learned quantum field theory long before we have a standard way on the textbook, I was like, take me a second to figure out what he's talking about, but that process is also quite interesting. Yeah. So, people can have a different way of dealing with a problem. I want everybody to pay attention and kind of like listen and discuss with each other. And then tomorrow, we're going to dive in a little bit on the structure. And so we might talk a few things on the common calculation on the lattice, then a little bit about the proton spin and mass decompositions. And if we have more time, we can do a little bit more advanced lecture. And if we are still working on the Wednesday, that's also fine. So don't feel like you have to rush and do, right? Take your time and then what you can. And that's all I want to get from you. And then on Friday, hopefully you might be getting too tired by then for the whole week's lecture. Then I will just tell you a few things about what is really exciting going on in our field. There's a number of broken X, what we call broken X dependence calculations. And I will tell you a little bit about the current progress. And there are also quite a bit of challenge that we're still dealing with. And so that's where really new people can come in, bring in new idea and so on. Right. Any question about the plan? All right. All right, so let's start with the standard model and QCD. So as some of you might have seen this in some of your colloquium, like QCD is really kind of simple in a way that you can put it in the mark, but also complex in the way that we have been solving them for so long. We still not quite resolved them yet. And so if you look at the particle zoo, so there are a few species that we are particularly interested in, basically the quark sectors and then the gluons, right? And among the quark sectors, they actually, the uptar and downquark actually play a lot of significant roles in a lot of daily matter that we're dealing with. And sometimes we go on to study the strange and the charm, and then go beyond that, usually require additional effective tool to deal with the heavy masses, right? And so we really mainly focus on the strong interaction, and we can ignore the other forces and focus on solving problems involve these issues. And we deal with something called like SU Dewey gauge. If you take some of the glue theory, that's one of the things we do. And so it is. Let me see. I can get this to work. Okay. Oh, it's echoing. All right. I'm just going to pause here. And so there is this game about QCD. And I always feel it's such a shame that nobody know about it until you go decide, I'm going to study physics. And then you have to take like a year of PhD classes before you can actually learn QCD, or sometimes longer, depends on the university, right? But some of the rule of the QCD is actually as simple as you can put it in a game, right? So this is one of the things I did for my NSF career award, is sort of like come out in the idea of, I saw my kids playing games all the time on my phone when they were little. And then there's this nice crash, something called Candy Crush. I don't know, people still playing that these days. I think it's like my generation was really popular. Everybody was playing them on the subway. So this is kind of idea coming to me when I was commuting. When I was in Berkeley, I was commuting like 2 hours to Berkeley Lab from Silicon Valley and back and things like that. Like sort of like a way to communicate with my family about what I do. And a little bit also show people that actually a lot of physicists now that's scary, right? We all get into physics because we like the simple rule. There's a rule, there's regulation, and and things like that. And those kind of fit game design pretty well. And so that's how you come up with such an idea. So you can get the link on the file later on. But I just kind of like this is something like one can really think about the simplicity part of the QCD that follow the rules. That's good. And then there was some undergrad help me design. All right, so then I like this photo. And so we host a annual Lattice conference at Michigan in 2018. And then we are beta testing the game. So this is my older daughter at the time, it's probably five years old. And my PhD advisor was learning from her how to play the QCD game, which I thought that was funny. Yeah, okay, I'm gonna skip some of this. Right, so, all right, so like I say, the QCD is the strong interaction for the quarks and gluons, right? So those are the 90% of the player that we think about. And so you probably see some of this part. One of the reasons the QCD is complicated because it's coupling constant that we call strong coupling constant, S for strong, and it's a function of the energy. So Q is energy here. And so unlike QED, which is a constant, so and it's small, we like things are small, we can explain things as small, right? And we still do so, right? At at high energy scale, when the strong coupling constant is small, we do a lot of perturbation scale and titillation. It goes really well. And these three gentlemen to hold Nobel Prize for demonstrating that, right? A different experimental process, you can connect them with the perturbation calculation very well. And as we move on to the lower energy, so a lot of those problems people saw, and they are like moving on to higher precisions. In the lower energy scale region, there are still a lot unknown, a lot of low energy property that we don't know as well. And this is where we are hoping to be able to contribute by doing things like this QCD, right? And so why do we care about this, right? So there are a lot of wide scale application for those low energy scale physics. Here, just a few examples. And for me, myself, is really interesting the structure that make out the hadron. So where did the mass come from, and how does the spin add up to 1/2? You know, how much is that composition coming from quark and gluon? That interests me. Here at Justin Lab, there's also a lot of effort on trying to imaging the proton to study the three-dimensional structures. And I also pick up some interesting studies, something called proton distribution function, which is universally go into a lot of different calculation, not just the high energy at LHC when they try to find new physics, but also a lot of standard model baseline, like things like in the IceQ as well. Searches, they also need to put in the proton distribution function as input to study what they saw, right? So there's a wide range of application there. There are also some of our colleagues also try to study how do we see the nuclei form, right? At what particular binding energy, right? So we all know that if the carbons only become abundant because there's this nice chemical structures that you can form the right binding energy that we end up with a lot of carbon. Without them, we could probably not the carbon, maybe we are a different kind of life form, who knows? And so they are studying the property of the light nuclei and try to study how if you have a proton in the nuclei, how the property got changed and so on. It's kind of, unfortunately, a lot of day-to-day elements is like that, right? And they can also have astronomical applications. So for example, the center of the neutron star, nobody really quite know what they are exactly. I mean, we definitely know there are a lot of neutrons that obviously play important roles, right? But there have been a lot of discussions since the 80s about the strange quark or strange hadron can form in a way to alternate the property of the neutron star evolutions. And then there have been a lot of discussion on and off every time people find new limits for the neutron star masses and things like that. And so be able to narrow those down would be also very helpful. But doing the what we call hyperon is the hadron make out the strange quark experiment is really hard because hadron decay in nature due to the weak forces. But we can put them stably created on the supercomputer until we want it to decay, right? So there are a lot of property we can do reasonably well, right? So there are some of the attraction, but it also comes with the difficulties, right? Because we all learn from physics, we always go back to let's talk about the ground state, the lowest energy state. And in classical physics, sort of simple, right? The vacuum of the ground state is nothing, and you start from there. But with the QCD, it's like a evolve. You kind of have this quarks and antiquark pair that pop out in the background. So the vacuum itself is not a steady frame, right? It keeps changing. So how do you try to learn from something on top of thing that's ever evolving and so on? So that's sort of make the job more complicated, and that's why we haven't really quite solved it yet, right? So this is not as simple as we were hoping to be able to deal with in the traditional pencil and paper solutions, and that's why we're looking at the Lattice QCD. And so in a snapshot, it's sort of like very sure you take some sort of Feynman diagram of your interest, and then you put it, you try to write code around them, and you put it on computer, and then hopefully we can solve them non-perturbatively, right? So that's sort of just for that, right? Right. So this just kind of come up with the Wilson come up with the idea in the late 70s. We were trying to solve different issues, but it was proposed that instead of solving continuous 4-dimensional space-time, as we would usually do in the field theory, he would discretize space-time. Right now, you introduce some sort of resolution issue, right? So what we call lattice spacing. You can think about this like a pixel on your pictures of the phone, right? You always want the pixel to be as small as possible, but you also take up lots of memory and so on, right? So similarly, as we do the calculation, right, we want this resolution to be as fine as possible. That will close to describe the real world, but the smaller the lattice spacing, the higher the computational cost. And because this is a 4-dimensional space-time, so it's roughly scale like so you want to decrease lattice spacing by a factor of 2. That's like 2 to the 4 by naive scaling, right? We do some trick with them, but still you can imagine like a year calculation can be very quickly turned into 10-year calculation, and nobody want to do 10-year PhD. So that is a problem, right? And then same thing, we will have some sort of box cutoff, right? Supercomputer is powerful, but again, you cannot deal with infinity degree of freedom. So we have some sort of cutoff in our 4-dimensional box, and we just kind of need to make sure that the box is big enough that we don't alter the property of the hadron we try to study. So how do we know that? Well, sometimes we don't know, so we study multiple boxes to see sizes, to see whether the property change. We can even do extrapolation and to get us closer to what the answers are. And then, then over time, there are more and more people study something similar. You can also look at literature to see in what range people might see problems and try to avoid from that if you don't have the resources to do multiple calculation yourself, right? And for the new quantity, then you kind of just have to kind of guess around them and study on your own more carefully, right? And so the quantum masses is another factors. Right, so in nature, we know we sort of know what the quantum masses are to some precisions, right? On the lattice calculation, we also have quantum mass as a parameters. And as it turns out, the lighter it gets, the more expensive the calculations are. It kind of something we call critical slowdown. It kind of slow down the inversion of the propagators. And so very often it's actually cheaper to calculate multiple heavier quantum masses and extrapolate to the physical quantum mass than directly do the calculation on physical quantum mass, right? And so sometimes we do take that limit. And so occasionally when you look at lattice calculation, people might mention, in addition of mentioning quantum masses, they might mention in terms of pion because quantum itself require renormalization and field theory stuff. So you refer this as a pion masses dependence, lattice spacing, and occasionally volumes. Yeah, but most of calculation know to avoid the value that's too small that can give you big problems. Right, so if you put it in the more formulae, right? So that's the path integral. So if you know an observable that you're interested, right? You want to do the path integral, you sandwich them in between whatever your ground state is, right? And then you will be doing such a path integral, right? And then you have like actions in terms of x, right? And so because we discretize space-time, so now you have more way to write down the QCD action and continuum. For example, I can add an order A term, right, or some weird operators that are proportional to order A, and I go to the continuum limit, the operator goes away, right? So I recover the same continuum limit, right? And obviously not all operators that give you good property, right? You want to add operator because that's another term you have to compute on the computer. So you want to think about, does it bring you some good property that simplify your calculation, right? So there are a lot of, in early days, in the 80s and 90s, there are people think about, what new operator to add. Sometimes you improve the property, and sometimes you recover the chiral symmetry at finite lattice spacing, right? And that helps with people who try to study like a property that's really, really important to the chiral symmetry, for example, right? So as a result, you have here like people are using various different lattice spacing, depends on the physics of their interest, right? And they can do the same thing with a glue and do the same thing with a quark, right? And it turns out the quark actually quark action have more impact in a lot of hadronic observables. So you hear more about the action people using quark more frequently. Oh, sure.
It on?
Yes. Okay. And then same thing here. You want to make sure the lattice spacing is small. So that's a ultraviolet cutoff, and the value is large enough. And then maybe if we have enough resources, we should do multiple lattice spacing and multiple values so that we can get to the right continuum limits. Oh. Right. So this has been proposed in 70s. So why we haven't solved QCD yet, right? And so there's definitely some progress that's limited by computational resources, like a lot of computational science. So this is like the state of the art 80s. I don't know whether you guys, maybe your parents or your grandparents may have some sort of giant computer in their garage, like my in-laws, still keeping something that's not working but huge. It's like it's kind of state of the art game you can do, which is just using the arrow to move around some of this. To today, you have very tiny device, right, SPS or something else, and have lots of graphic vectors in there. So obviously the computational resources are improved significantly, and now we can do a lot more today than what we can do before. So that's definitely something great, right? And then another thing that the field have evolved greatly is we also work with people who are outside physics department, like people in computational science, applied mathematician, who often bring in interesting idea in algorithm. And one of the things that's really, I will get to in a sec. One of the things that's really interesting is there are algorithms who people think is stupid and useless, worthless at the time when they were invented, 100 years ago, and now become really useful in today's computer, because who knows, you're going to have a lot more faulty, operating power than you have in terms of communication and computer. That would just never happen before. So another moral of the story is I learned about all these stories, like you might have a great idea, may not be appreciated at your time, could become very useful later on in 100 years or decades later. Sorry, questions?
Hello. Why is it that you use the pion mass?
Pion mass, yes. So the quantum mass, so we have a parameters in the action that's kind of associated with what we call bare quantum masses, but it's not exactly the quantum mass, because it goes a little bit complicated, right? So if you learn about field theory, there's a renormalization involved, right? So that quantum mass is a parameter we put in the action, right? Require additional renormalization process to be able to give us what the true quantum mass is, right? But when you look at the pion mass, which is made out of the quantum masses, right? We don't have to deal with those renormalization issue, right? So when you start to deal with the renormalization issue, you have to think about the precisions and then what way, how the scale setting. So there are a lot more parameters involved that you might be if they have different procedure, you could have slightly different quantum mass determination. While pion mass itself is a physical observable, right? We come up with a calculation, and it's a very standard way of extracting them, right? So that one of our tutorial will be extracting something called two-point correlators. And those can be directly extracted from the message. You don't have to worry about, oh, this glue is doing this calculation differently from another group. And lattice people do calculate quantum masses. And so, but there you have to be very, very careful about how you do the calculation, and you have to run the scale because quantum mass itself is a scale dependent as well, how you run them. What is your starting point? So you get into a lot of complication that maybe we don't have to deal with for now.
What do you mean by scale dependent?
So the quantum mass itself is not a fixed, like all the masses actually, right, in QCD, quantum masses, yes. So like the strong coupling constant is a function of energy, so is the quantum masses. Yeah, so often when we look at PDG, the particle data group, it usually give you a common scale. When you look at light quark and like up quark, down quark, usually give you somewhere about 2 GeV scale masses, right? And that mass can change if you try to evolve your energy scale, right? And then strange quark, strong quark, we look at them at a different scale. And then heavier quark, we look at it like masses of and Z or something, Z boson and other things. For whatever convention reason people find them in the first place.
Thank you.
All right. So how do you do a lattice calculation? Obviously, you need some sort of computational resources. And so in US, we have a little collaboration called US QCD. So a lot of the lattice QCD people in the US sort of come together, and we had a proposal to DOE do a call called SciDec, and we purchased some cluster around Fermilab, Jefferson Lab here, and also Blue Heaven Lab. And then they want a cluster that for lattice people to use. So we write proposals, and we have meetings to discuss them, and then we have a committee to allocate the sources that people can use. So NSF and DOE, they also invest heavily on the supercomputer center. NSF now have do something called access. They tend to put their supercomputer associated with the university, while DOE working with laboratory, so that everybody's solo covered. And so one of the biggest resources from NSF is somewhere at Texas, as TACC. So one of the things that's really interesting is they tend to have local thing to it, because in Texas, so their storage is called range, and then their computer Stampede 1, Stampede 2, and things like that. And in DOE have machines in a lot of different laboratory. This is a picture from something called NERSC. It's in Lawrence Berkeley Lab. They also have a powerful machine that's currently top number 1, top number 2 in Argonne and Oak Ridge National Lab. And so what I really like about the NERSC is they like to put the scientists on their computer names, and they alternate male and female scientists in a way. And one of the machine I use quite a lot, given my calculation a while ago, is something called Corey. And so I still have this picture around. And so basically you come up with ideas, and then you sort of write proposal, and they are like some sort of committee evaluate the proposals, and so you can get the computational resources. But if you are young and energetic, it's me long time ago when I was a PhD student at Columbia. I was doing the calculation that the glue, nobody else in the group cared about. And then with my advisor at the time was putting together his own supercomputer. So I actually put together a tiny bit of cluster right here, and I was babysit that to feed my, this is the computer I got most of my graduation data from, right? But you could do that if you are young and energetic. I can't imagine myself doing that again. There are also a number of software. So the QCD code is getting really complex, that we actually have a community code. And we do try to, obviously, again, right, you don't want to reinventing the wheel. There are a lot of tools that people develop, you want to take advantage of that, especially you can use them quite reasonably well. And so as a US QCD. So we have a collaboration. You can look into the code here if you like. So they have different labels of applications. Some of them more lower label, that's more universal, to some physics code that we actually do measurements, what we call do measurements, like putting observable together and so on the top yellow labels, right? So most of my code is kind of something called Chroma. So you can see some of the tutorial that mentioning this name. And so basically I only think about, that path integral process rather than a lot of speed up, which is sort of in the lower label. And it's great that everybody got to do what they love to do. There are people really good at speed things up and they want to think about those problems and we develop a tool, then I can just kind of call them and I can focus only thinking about the physics itself, right? And there are also a number of tutorial available on learning how to use those resources. And some of this, the website still have the tutorial material, but unfortunately they lost the videos. And we have another summer school in IT about 10 years later. And we do put in a number of the lecture and tutorial material there. So if you are interested, this will be on the website you can look at, right? So once you have those, the next thing you need to think about is what sort of QCD vacuum that you're going to use, right? So it's not just kind of one kind. I mentioned that you can have different actions, combination for the glue and the fermions, right? So that can come into, depends on the physics you want to do. And then there are different flavors as well. And so what we do, I mentioned, right, the QCD itself is kind of ever evolved, right? So, but we all learn from doing physics, you take something stable and then you do the calculation. And so what we do here is basically we take sort of snapshot of 4-dimensional space-time snapshot, right? So it's sort of like taking a snapshot of the QCD at a different time, and then you do the calculation on each of them. Right, so I do a calculation here, I do another, repeat the same step, but different vacuum, and I keep doing this, right? And you can imagine this is a little bit like making a movie, right? You have enough frames, you put them together, and that will describe the nature as well as possible, right? And again, right, the longer the snapshot, the better as well, right? Because so that you reach that, the true QCD background average as much as you can, so you can. And those can be, so a lot of collaboration have been spending a lot of time. That's where a lot of, so if you are thinking, some of you are looking at the archive and you can see like most theorists doesn't write paper with a lot of people. Lattice QCD people tend to write paper with like 20, 30 people, like, which is a lot. A lot of them coming from generating those configuration because you cannot publish paper by, this is QCD vacuum. Why would I care, right? It's only useful when you use them for various interesting observables, and that's where like you really need a big group of people to figure out a lot of problems generating those vacuum, which is a very non-trivial and large resources required. And after you've done all that work and do all the calculation you need, right? And then what do you do with those configurations? They can be still useful for other people. And so what people do is they try to formulate some sort of international lattice data grid. So you have a universal data format, and you put it on internet. So whoever want to use them, they can download that, right? So you can use them to test your ideas and play with something else, new idea that people haven't thought about. And so you could download it like download everything else on internet, right? And they have multiple data grid. Okay, yeah, that's not working. Yeah, so you have, and we have had that multiple server around the world to make it download a lot easier, right? And then when I was postdoc here, we are doing some sort of problem that nobody else cared about. And then we need a much finer resolution in time and while you keep the space on your course. And that's sort of Bohr symmetry, which is, you should know, always, when we Bohr symmetry, always bad thing coming in physics. But we are really interested in the problem that with the final time resolution. So we sort of deal with that consequences, and then we try to get something really, really difficult to get on the lattice QCD by having finer resolution. And so things like that, you sort of have to roll up your sleeve and do it yourself because nobody else there is generating this type of lattices. So it does vary a little bit, yeah. And then after you have the vacuum, the next thing is you will want to do something called generating correlators. And first you want to, you have a fermion action, so you invert the Dirac operator, and as you get to more realistic problem, the rank of the matches get much higher. And so what you do is say, if you have a imagine this is XYZ, and this is the time dimensions, right, on our QCD vacuum. You might create a hadron, say I want to study the property of protons. I create a proton, a particular space-time, and I propagated them and analyze them another space-time. And in between, I recall the time dependence property. And then I have some spin and momentum, other typical thing that we try to identify the particle with. And then I can study the masses like this. And if I'm interested in the property of that, then I would put additional proof. And that proof would define different kind of observables later on, right? And they are various different operators. They are not unique. You can, I say you can write down many or different type of operators on the lattice, but the simple thing that's also used in a continuum can also very directly apply on the lattice as well. And then after that, you will be doing some analysis, either extracting masses or different kind of coupling or what we call matrix elements. And so a lot of time we spend time study something in what we call Euclidean space. So we have some sort of exponential time series that we're dealing with, and then the energy or masses, it tend to hand out in some of this exponent here, right? So we want to do a little bit of this exercise later on. Let me see how much detail I want to get into. Okay, yes, here, right. So as we put in the operator, right, we only have control in terms of their property, right? Their spin, how many quarks involved, and so on, right? And but there are also a lot of radiating excited state which will couple with that. So you don't always just create one state, you create a summational state, right? So it's very typical of the quantum mechanics. Okay. All right. I should take a quick. Let me wrap up this, and we take a quick break. So you basically sum up. You basically get a number of. If you pick your operator well, which the operator here I use J, and the N is an eigenstate. If you pick it well, it will be dominated by the ground state, right? And there are various different tricks that we do on Lattice QCD to try to make sure that happens as much as possible. Or you are interested in excited state, then you should be try to pick certain operator that have better overlap there. But generally speaking, you end up with something that's kind of dominated by the ground state because of exponential time, right? The lower the energy, the higher the larger time, the property will go to, the masses will go to, the correlator will be dominating by the ground state. And then say if that's the ground state is what you're after, like protons, and you can imagine you can form some sort of simple relation, assuming a larger time. So this is something called effective mass part. A larger time will be dominated by only one state, and that will give you something like a ground state. But earlier time, you're going to have some mixture with the other state. So that's where you see some, this is not quite where we behave here because there are additional state here, right? So this is something we're going to be doing in a bit. So I think we should take a quick break, right? But the last thing is to talk about the systematic, which I mentioned in the intros, and we should take a quick break here. Okay.
Questions, maybe?
So since the lattice is finite, so are there any boundary conditions that we impose on the fields on a lattice?
Yes, yes. So typically the periodic boundary condition on the space direction time might vary. Most of the time periodic, but there are occasionally people use anti-periodic to study various different properties. Yeah, so that's usually the simple one. And there are tricks one can do to, there are spatial boundary conditions for spatialized problem as well. That's only used by a few, yeah.
And could you also talk a little bit about how the E tending to 0 gives rise to UV cutoff, and the finite volume gives rise to infrared cutoff?
Oh, so the latest, so the distance basically corresponding to, like, is a distance corresponding, distance of the problem in the scale, right? Corresponding to inverse of the energy. right? So the smallest distance is the highest energy cutoff, right? And then the largest value that corresponding to the smaller energy cutoff. That's why it's ultraviolet and sorry, let's see. Yeah, ultraviolet and the ultraviolet, yeah.
Yeah, so in your slide with the QCD vacuum, there was something like gauge configurations.
Yes.
So, what do you mean by gauge configurations in that slide?
Yeah, it was just the snapshot. So it's like so when we simulating the vacuum, we do a vacuum simulating vacuum, and then we take the snapshot, right? So this is a 4-dimensional space. The vacuum, the file we save, and then we use, and then later on we can take it out and do a calculation corresponding to this particular space-time vacuum. And then you do repeating for the next one. So you can take out the integral here.
I think what I don't understand is like, how is the gauge coming into play there?
Oh, okay. So okay, maybe, hold on a sec. I think this, so if you think about this like statistical problem, right? So the action here have gauge action, you have gauge gluon field, right? And then and the quark fields that correspond that devolve into the QCD action there, right? And then and you mean like what do we call it, gauge configuration?
In the QCD
Yeah.
vacuum, what do we mean by?
Yeah, so actually other than its gauge theory, I don't think I ever think about where the name come from. We just call it gauge configuration. And when I started giving lecture, I feel like nobody know what gauge configuration is, right? It's like, what does that mean? So I like to call it QCD vacuum, and which is basically a mixture of all possible loops or interaction with the quantum gluons, which is what it is, right? Without the operator itself. And so, yeah, somebody probably, before me determined that name. I was as a student, I've been using that name. I never think about why we call it gauge configuration. Well, probably because it's a strong gauge interaction it coming out from, and configuration is like, I guess it's more formal in the way that, in sales. Next shot. Yeah. I can try to Google. Somebody can try to Google. Maybe Wikipedia have a better. Yeah, but I never thought about it. Yeah, that's a good question. I never asked for that question.
Just my last question. So, when we move from Minkowski space to Euclidean space here, is it like a Wick rotation or? Like...
Yes. Sorry. Yeah, it's a Wick rotation, and so. It's a re-rotation, that's right. And then so sometimes the operator itself also change a little bit as well. Yeah, it depends on what you do with that. Yeah. So the field itself changed. So the imaginary time disappeared, and we are now with the real time. And sometimes the gamma matrix structure also changed to preserve that in physics.
When you move to the Euclidean space, are there any complications arising due to the pole terms or something like that?
Yes, there are definitely issues that happens, right? There are things that something called real-time information that we can't quite do well on the lattice QCD because we only deal with, you can think about a lot of lattice QCD like statistical problem, right? We deal with the demo, like after everything is equilibrium, right? And we do a lot of calculation there, and we do something very well there. But anything before that, we don't do as well, like time-changing properties that we don't do very well. There are people thinking about maybe that's something that quantum computing would be better doing if, that's kind of physics that really interests you, right? But for me, I can live very well in the equilibrium region. There are plenty of things for me to do there. Very good question. Thank you.
Yeah.
You have told that we have to do some exercise, right?
Yes.
Are we gonna do lattice related calculations in Jupyter?
We're gonna do a little bit about the analyze part I mentioned. So okay, sorry. Let me see what's the good slide. Yeah. So we're gonna take the We're gonna first do something called Gen I as a Gen I exercise, and then we're gonna do the analysis to try to get ground state out from the data. Yeah.
Okay. Can we also do PDF calculation, or can time allows to do PDF calculation?
PDF calculation. We might have time to do a little bit of some of the what we call 3-point function that's related to extract the useful matrix element for the PDF input. Yeah.
Okay. One general question. How you prepare your lectures? Like, if you have to give a lecture, how you prepare it? Like, you have very good presentation skills.
Thank you. So it's sort of like, well, first of all, when you are a theorist, you usually get a lot of interview before you get a job. So you do have a lot of practice. And over time, you learn to like what's sort of when you give a talk, right? You want to think about what exactly what the audience to get, right? There are people want to dazzling the audience. They can put in a lot of jargons, and I always find that people just fall into sleep when you do that. So I try to like use less technical term like QCD, vacuum, snapshot, things like that, animation to more relate to the people rather than to sleep. And then people tell me they like those descriptions, so I use those, and I try to not use the other things that put people to sleep. So be able to come back and do in person is really useful because you can actually see what people are doing, and things that I saw people start to daze out. Feel free to do so if you get really boring. I know that's something I should work on and rephrase them or using different way or presenting them somehow in the future. Yeah. So.
Thank you.
We'll take a 10 minutes break still.
For that?
Doesn't
work. 5 minutes break, but before that, check out the Slack channel. There is a new message about the seminar, so you have to see the form with a title and an abstract for your participation. It can be either a seminar or a poster. You need to choose, and you also need to tell us if you need us to print your poster. You have a week to write all that, and the link is on the Slack channel. And if you have any problem with like accessing the link or anything, just let us know.
It's free, our lecture, and you can get back to the discussions after. All right, with no further ado, Huey-Wen Lin will keep going on with her lecture. Please, Huey-Wen.
So, all right, so I'm just gonna wrap up here, then we can get into the tutorials, right? So this is one of the exercises we'll be doing. And if you want to think a little bit more about some of the problem analytically, you can also, there's some exercise they can work on. And then at the end of the day, like I say, right, we do introduce some artificial scale that does not exist in the continuum, and we want to get rid of that before we claim that whatever the quantity we calculate, it's something that you can use in the real world, right? So ideally, if we can do this, that would be the great. So that's something we call continuum limit, right? So the pion mass is not directly calculated, the physical pion mass, we might calculate a number of them and do an extrapolation. And we do multiple physical values, and then we extrapolate that to infinity or make sure the quantity is not changed because of that, and similarly with the resolution. And so here's one other example that's done by a collaboration used to be in Europe, now it's US. It's called B&W, it's a very clever name, everybody remember them. It's from the initial for the 3 institutions. And so this is something published a while ago where they do multiple lattice spacing, and they also do multiple pion mass calculations. And then so they were doing very simple hadron calculations on nucleon, and then omega hadron, which is 3 strange quark put together, the spin 3 half. And so there they will simultaneously extrapolate them to where the physical limits are. And they were doing such a great calculation, very precise calculation. And at the time, that's important enough to get on science. And sorry, that one. Okay. And then one of the things they do is they, in our calculation, we had to kind of set the scale in a way, right, to fix our scale. And so we try to use the physical pion masses, pions and kaon masses to say our light quark, up-down quark, and strange quark, and everything else is predictions, right? So the box here is what the number that's taken out at the time from the particle data group. And the rate point here are their calculations. So they were able to very precisely reproduce, and in some cases have better precision at the compared with the experiment known at the time, right? And so there are a few examples. So what can you do with Lattice QCD? So there are a few things that we like to do is to provide higher precision for some of the known quantity. For example, one of the calculation I did with Raul, which is some of you know him here. He used to be a physicist here with ODU. Now he's in Berkeley. And he was also a student at the University of Washington when I was a research assistant professor there. And together we look at something called pi-pi scattering. This is one of the simplest case, but experiment, they haven't been experiment for a long time. And the experiment predict like something really large error bar, and then people weren't able to repeat the experiment due to the new safety measure and stuff like that. And so we were doing a calculation together. It's kind of his intro exercise to Lattice QCD, but turns out that we made some nice prediction at the time. And then we also look at the Trump-baryon spectroscopy. And at the time, this was 2012. A lot of LHCb results haven't come in yet. So we actually made we have some, reproduction with the known masses, and then we made a number of predictions at the time. So that was before LHC turned in, which is cool that we are able to make some of this prediction back then. And then you can do similar thing with the B quark as well. So again, this is done a while ago, but we are able to make some interesting prediction and so on. So I'm going to skip this. There were just not enough time. And if you're interested in more complicated other than ground state, I have a few slides here, and I have some videos I can link that to you as well, so you can know more about that. All right, great. So we have made quite a bit of progress. And then like I say, right, this is really how much you learn from the tutorial. There's no need to feel like, if you're interested, feel free to do a little bit more exercise, continue. And if you're not, we should at least need the GenI function for our next exercise. And then, so if you guys would like to check or somebody like to share their function, feel free to do so. And we have some minute for question. We can do this in the group setup, but if you are tired and want to stretch, I totally understand. We can just, if you have further question, I will be here for another 15 minutes.